Friends, we will continue with the discussions on shear center. This is lecture 27 on module 2, where we are discussing advanced structural analysis, shear center 2. Now, we will take up the second example problem, where the section now is a channel which has one axis of symmetry as marked now. So, I can say this is axis of symmetry. Let us say the dimensions of this is B, thickness T, and depth of the section D. Let us say this is my resultant shear force V 1, this is resultant shear force V 2. For the applied load V at the shear center C, which is distance E from this axis. So, now to find V 1. V 1 is tau d A, which is V A y bar by I t of d A. Let us consider a strip which is x from here and whose thickness is dx. So, area under consideration is going to be t into x, and dA is going to be dx into t, and y bar, the strip distance, is going to be d by 2, that is this distance. So, therefore, now V 1 is V by I t integral d x dx t into d by 2 A y bar. So, which is then integrating this from the limits 0 to b. So, V by I t integrating 0 to b t square d by 2 x dx. V 1 now can be computed as V by I t t square d by 2 x square by 2 0 to b, which is V t by 4 I b square d, that is V 1. We also know by symmetry this is also equal to V 2. Let us neglect shear taken by the web. So, let us take moments about C. So, V into E, which is anti-clockwise, will be now equal to V 1 into d by 2 plus V 2 into d by 2. So, V into E is V t b square d by 4 I into 2, which gives me E as t b square d by 2 I. Let us take up another example. Let us say these are center line dimensions. Let us say this dimension is B, let us say this is B 1 and this is H, section has uniform thickness T. We agree that this section has one axis of symmetry and the shear center need to lie on this axis. Let us say this is the plane of application of V and this becomes my shear center C. Let us say that this is placed at a distance E from here and the shear flow will be like this way. So, let us call this as V 5, let us call this as V 1, V 2, V 3, V 4 and so by symmetry we know that V 1 is V 5 and V 2 is V 4. Now, I want to find V 1. So, let us take a strip which is at a distance Z, thickness d z, We know V 1 is integral tau dA, which is integral V q I t dA for the distance 0 to B 1, because that is the strip value 0 to B 1. Area is actually T into Z, and dA is actually T into dZ. Y bar, that is the distance of this from here, that is y bar. Let us say y bar is h by 2 minus B 1 plus z by 2, because you know this distance is h by 2. If you say minus B 1, you are here, plus z by 2 will give you the distance of this point from here. So, now let us substitute V 1, integral 0 to B 1 V by I t T z T d z h by 2 minus B 1 plus z by 2, which says V t by I, because there are two t's here in the numerator, integral B 1 h by 2 minus B 1 plus z by 2 into z dz. So, V 1 will be V t by I h by 2 z square by 2 minus B 1 z square by 2 plus z cube 6 limits 0 to B 1, which is V t by I h by 2 B 1 square by 2 minus B 1 cube by 2 plus B 1 cube by 6, which will be V t by I h B 1 square by 4 minus B 1 cube by 3, which can be then simplified as V t B 1 square by I h by 4 minus B 1 by 3, that is V 1. Let us say equation 1. Now, let us compute V 2 for this flange. Let us draw the sketch separately. This is axis of symmetry, which is at a distance h by 2 from here. So, let us consider a strip which is at a distance x from here and thickness dx, and we know that this thickness is t. and we also know that this dimension is B 1. So, now there are two areas here, okay, there are two areas here. Let us do for both. So, to find V 2, let us say first let us compute A y bar. So, B 1 into T into h by 2 minus B 1 plus B 1 by 2, that will be the distance of this center from here, plus h by 2 minus B 1 will be here, plus B 1 by 2 will give you this. Okay. Plus that is for the hatched portion here, and for this remaining portion it should be x into T into h by 2. So, which can be expanded as B 1 T h by 2 minus B 1 square T plus B 1 square T by 2 plus integral of this x t h by 2 for the length 0 to b. Let us compute the area is x t, dA is dx t, and y bar for this piece is h by 2. Therefore, V 2 is going to be V 2, let us say star, that is this part, horizontal flange, this part is star, is going to be integral V by I t x t t dx h by 2 0 to b, because that is the dimension of this 0 to b. So, which will be V t h by 2 I x dx 0 to b, which gives me V t h by 2 I b square by 2, which says V t h b square by 4 I, that is V 2 star, that is this part. So, let us find the total V 2, which will be V t by I B 1 B h by 2 minus B 1 square B by 2 plus B square h by 4. So, now equation number 2. So, taking moments about C, not taking moment about C, taking moment about A, where A is this point. We can write V into E, which is anticlockwise, which will be equal to V 1 plus V 5 into B plus V 2 plus V 4 into h by 2, which simply says that it is 2 V 1 B plus 2 V 2 h by 2. So, substituting for V 1 and V 2 in terms of V, we can straight away say E will be given by T B 1 h squared by 2 I b 1 plus b by 2 b 1 minus 4 by 3 b 1 square by h. Let us do one more example. The section is again a special section used for housing electrical cables or cable tray. Which is called as a channel bracket section. Let us say the dimensions are marked as B 1, this is B, which is as same as center to center. The section has uniform thickness T throughout and the inner dimension is H. As we now agree section has one axis of symmetry, therefore, the shear center will lie at this point. Let us subject the vertical load here. The shear flow will be this way to oppose the shear. Let us call this net resultant as V 1, this net resultant as V 2, V 3, V 4 and V 5. Now, to find V 1, we will cut a strip at a distance z from here and let this be dz. And for finding V 2, let us cut a strip at a distance x from here, let the strip be dx. Now, to find V 1, which is integral for the entire area V q dA by I t. Now, area is T z, d area is T d z and y bar is h by 2 plus B 1 minus z by 2. So, therefore, V 1 will be integral 0 to B 1 V by I t T z h by 2 plus B 1 minus z by 2 of T d z, which is V t by I h by 2 B 1 square by 2 plus B 1 cube by 2 minus B 1 cube by 3, which can be said as V t by I B 1 square h by 4 plus B 1 cube by 3. which is V t B 1 square by I h by 4 plus B 1 by 3, that is V 1. Now, to compute V 2, take this strip into consideration. So, to find V 2, now we are looking for this is an axis of symmetry. I am cutting a strip here at a distance x from here of dx. So, we have to look at this area and a y bar of this separately. So, there are two pieces here, one is horizontal, one is vertical. Let us work out separately. So, q is actually a y bar. Let us say B 1 into t is the vertical strip. This distance we know it is h by 2, and this of course we know it is B 1. Therefore, the distance will be h by 2 plus B 1 by 2. Now, for the horizontal strip it is simply T x, and the distance of this is h by 2. T being very small, we can straight away say that this distance is as same as this distance. So, dA is T dx, therefore, V 2 V by I t integral 0 to b t B 1 h by 2 plus B 1 squared by 2 plus x h by 2 of t dx, which can now say it is V t by I B 1 h b by 2 plus B 1 square b by 2 plus h b square by 4 after substituting the limits. One can also calculate I for the entire section. We will do it here. So, the moment of inertia for the entire section can be calculated as T h q by 12, that is for the web, T b 1 cube by 12, that is for this portion as well as the above one. Then parallel axis theorem, T b 1 h by 2 plus b 1 by 2 the whole square. There are two elements of this, plus b t cube by 12 plus b t h squared by 4, again two elements of this. Once I know I, now taking moments about point A, we can say V 2 plus V 4 into h by 2, because they will cause a clockwise moment about this point. V 2 will cause a clockwise moment minus, this is going to cause an anti-clockwise moment V1 plus V5 of B will be actually equal to, this will cause again clockwise moment, which will equal to this moment, which is V into E. So, one can say V into E plus 2 V 1 B, because V 1 V 5 are identical, is actually equal to 2 V 2 H by 2. So, we have equations for V 2, we have V 1, and V is a known value. By solving, I can find the shear center distance E, which is marked from this point, which is calculated. So, E can be computed. Let us take one more example. Which we will take a curved section let us say this section has an angle which is extended to be 2 alpha, and let the radius be r, let from the vertical the strip be beta, and let us now cut a strip at an angle theta, and let this angle be d theta. So, this becomes my axis of symmetry. Let us say my load is applied here, and let this be the distance E, the distance of shear center. So, now the objective is to find E, locate the shear center for the section. We know Q is A y bar, which is actually prior to that tau is V by I t, varying from beta to theta y dA, because that is my area under consideration, which will be V by I t beta to theta r cos theta into r into t d theta. Therefore, tau is V r square by I, okay, sin theta minus sin beta after applying the limits. Now, the elemental shear force dV will be tau dA. So, dV will be V r cube t by I sin theta minus sin beta d theta, because that is my dA or d theta, because dA is r d theta. Now, I take moment of this force about the shear center. Let us say dm is an elemental strip, V r 4 t by I sin theta minus sin beta d theta. So, now the total moment m will be integral beta to pi by 2. Please see the limits here, it is varying from beta to pi by 2, but twice V r 4 t by I sin theta minus sin beta d theta, which gives me 2 V r 4 t by I minus cos theta minus sin beta theta, applying limits beta to pi by 2. We also know from the figure that pi by 2 minus beta is alpha, that is this angle. This angle will be actually alpha because the total angle subtended is 2 alpha. So, using this relationship, since pi by 2 minus beta is alpha, let us rewrite m as 2 V r 4 t by I minus cos pi by 2 plus cos beta minus pi by 2 sin beta plus beta sin beta, which says m is 2 V r 4 t by I cos pi by 2 is 0. Therefore, cos beta can be said as pi by 2 minus alpha minus pi by 2 sin beta is again sin pi by 2 minus alpha plus beta sin beta, that is pi by 2 minus alpha multiplied by sin pi by 2 minus alpha. Applying trigonometric rules, we can say by I this becomes sin alpha, the second term becomes minus pi by 2 cos alpha plus pi by 2 minus alpha cos alpha, which can be 2 V r 4 t by I sin alpha minus pi by 2 cos alpha plus pi by 2 goes away minus alpha cos alpha, that is my m. So, now this m should be equated to V into E, okay, because we are talking about at the center, we have taken moment about this point. Okay. So, V into E should be equated. So, V into E is 2 V r 4 t by I sin alpha minus alpha cos alpha. So, one can now find E as 2 r 4 t by I sin alpha minus alpha cos alpha. Provided we know how to compute moment of inertia for this segmental piece, we will be able to compute the shear center distance from the center of curvature as shown here. Let us take up one more example and see how quickly we can compute the shear center. Let us do by some other quick technique to find down the shear center. Take the same example of a channel, but we do this problem slightly in a different manner. Let us say this dimension is 30, this dimension is 40 and this dimension is 120 and the thickness is 2. We know that this has two axes of marked like this, out of which one is axis of symmetry. So, shear center need to lie on this. Let us say this is my plane where the resultant force need to be applied. So, I take this distance as E. So, the shear flow says this is V 1, this is V 2 and this is also V 1 and this is also V 2 by symmetry. We already know this. Assuming linear variation of shear in the webs. So, assuming linear variation of shear in the flanges, tau max 1 is actually, let us say the force V is applied, V by I z, thickness is let us say 2, it is V 80. So, 29 into 2 is the area of this piece, no, this one. The distance could be 60 minus 29 by 2, which gives me 2639 V by 2 I z. Therefore, tau average will be half of this 2639 V by 4 I z, because we have assumed a linear variation. Similarly, tau max 2, that is for this piece, will be V by 2 I z. The piece area is 40 into 2 and the distance of C G is 60, which gives me 2400 V by I z. So, tau average 2 will be 1200 V by I z. Now, I can easily find V 1 is 2639 by 4 I z into this area 29 into 2, which is nothing but 38265.5 V by I z, and V 2 is 1200 V by I z into the area, this is V 40 into 2, which gives me 96 10 power 3 V by I z. So, now I have V 1 and V 2. Let us take moments about A. We know it is going to be V 1 into 2 into 40, because V 1 and V 5 are same, plus clockwise. So, plus V 2 into 2 into 60, that should be equal to V into E. Let us substitute back 38265.5 V by I z into 80 plus 96 10 power 3 V by I z into 120 is V into E. V goes away, therefore, 3061240 plus 11.52 10 power 6 will be E I z. So, now let us see how to compute I z quickly from this figure. I z will be 2 into 29 cube by 12 plus parallaxes theorem 60 minus 29 by 2 the whole square, 2 such pieces plus B d cube by 12, that is 42 cube by 12 plus A k square 40 into 2 into 60 square, again 2 such pieces plus of course the web B d cube by 12, which I get I z as 11.12 10 power 5 mm4. Substituting in the above equation, E is 13.11 millimeter. So, friends, let us look at the summary. Shear center is a special location of the cross section. It lies on the axis of symmetry. Preferably, load should be applied at the shear center to avoid twisting of the cross section. We have seen examples to estimate shear center for sections which has one axis of symmetry, because shear center will lie on that axis. We will also take up examples to estimate or locate the shear center where there are no axis of symmetry, how they can be obtained in the next lecture. Thank you.